Okay, so we finished the last video with current. So current is just the flow of electrons. However, we have to have a potential difference. Without a potential difference, we talked briefly about potential difference when we talked about static electricity, so be sure to go and look over those notes. It is a pretty tricky concept. So we had potential difference with static electricity, and that actually allowed for electrons to move. Think about rubbing your hair with the balloon. Because there's a potential difference, they could move from your hair to the balloon, making the balloon a negative charge. However, when we're talking about current electricity, we want a sustained movement of electrons. So we need something called an electric pump. Now, this is not a scientific word, which is why it is in quotations. But this idea, this pump idea, is actually very helpful. It sustains a potential difference. So if we have a sustained potential difference, more often, these are called, more scientifically, a voltage source. A voltage source. And a voltage source can either be a dry cell, a wet cell, or a generator. The batteries that you often think of, which are excellent voltage sources, so typical batteries are dry cells linked together. Dry cells and wet cells just mean that there is a chemical reaction going on. If you think about a battery that has leaked its acid out, you've seen evidence of that chemical reaction. So that is so what we should think about when we think dry cell, and think about a typical battery. So voltage is what we typically call potential difference when we're referring to circuits. Sometimes you will hear this called electromotive force. I don't use this terminology, but some of the references that I'll post on the website do use this terminology, electromotive force. The symbol is still the same. It's still a V, and the unit is a volt. Once again, we abbreviate that with a V. And that's it for voltage. Next we have resistance. And so take a moment and think about what resistance sounds like. So resistance, I have a funny story in my physical science class when I talked about resistance. They're like, well, do you mean to resist arrest? And I'm like, well, yeah, that's in one way that's true. But it's just something that gets in the way. You can think about a soccer player who is facing a defender on the field. That defender will resist the person with the ball to prevent them from scoring a goal. And so in circuits, it just means to impede electron flow. Impede electron flow. It depends on several things. It depends on conductivity. There's a reason we use copper wires in your houses. It's a very good conductor. One silly example to think of is if we used glass wires. Doesn't make a lot of practical sense in terms of breaking the wires, but it also is a terrible conductor. The copper wires allows a lot of electrons to flow. Also the thickness of a wire. Best example here is when you get home after a long day, what would you rather go home to? a front door or a pet door, and it's easier to go through the front door than the pet door. Same thing, if you have a thicker wire, it's easier for those electrons to flow through. We also have the length of the wire and the temperature. The temperature is often associated with light bulbs. Conventional light bulbs are awful at producing a lot of heat, which is why they're very ineffective in the long run. And so we do have a symbol for resistance. The symbol is R, and our unit is an ohm. This is a German last name. It's named after Mr. Simon Ohm, who essentially played around with a lot of resistors and determined what resistance depended on. We use a capital omega sign. That was an awful sign. Here, let me draw another one. We use a capital omega. Some people refer to this as like an upside down horseshoe. This is a Greek symbol that is a capital letter, but it's how we write a unit for ohm. So for a unit for volt was a V. Our unit here is omega, or an ohm.